Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So hello everyone, thanks for coming, and it's my great pleasure to introduce Emmanuel Kilsman, who is a postdoctoral research fellow at University of California, Berkeley, in the artificial intelligence group there. So Emmanuel obtained his master's and PhD degree from Germany, University of Berlin and University of Bamberg, respectively. And he has done some cool work in program synthesis and also found some cool applications that he's going to tell us more about today. Over to you, Emmanuel.
Okay. All right. So thanks for the invitation, Sumit. Thanks for coming. Okay, and today I'm going to talk about inductive program synthesis, and especially about inductive synthesis of recursive functional programs. Okay, so this is the agenda. I first of all introduce inductive program synthesis and inductive functional program synthesis, and then a particular approach, which I call the analytical approach. And then for the main part, I'll describe an algorithm, EGOT2, which I developed as part of my PhD research, and which induces functional programs based on a combination of the analytical approach and search in program spaces. Okay, and then finally, I will give you an impression of the capabilities of EGOT2 by some sample experiments. All right, so inductive program synthesis basically means the automated construction of computer programs, part of programs, pieces of code, from incomplete information such as input-output examples. So suppose we've got the three examples. Oh, I have a laser pointer. Let's see if it works. Okay, so we have here three examples of a function f from list to list. And f applied to the one-element list A is supposed to return the empty list. F applied to the two-element list BC returns the one-element list B. And f applied to DEFGH returns DEFG. So this is an incomplete specification of f because we've just specified three of the possible inputs. But it's quite clear which function is meant, I think, namely the function that removes the last element of the input list. Okay, so if we gave these I/O examples to a synthesis system, then it should come up with something like this implementation here. So this is a functional implementation. F applied to the one-element list returns the empty list, and F applied to a list containing at least two elements, x, y, and some rest list xs, returns the list with the first element x, and the rest list returned computed by this recursive call on the rest list. Okay, so this simple function is called init in the Haskell library, and we will have it on the further slides, so be prepared. It is called init. Okay, and we represent lists algebraically as it is standard in functional programming languages like Haskell or ML. So for the user-defined data types, we define a list by the empty list constructor, and a non-empty list by an element and a list put together by a constructor, which is denoted by a colon here. Okay. So that was a simple example, and what might that be good for? Inductive program synthesis. So there are different fields where it can be applied or could be applied. For instance, inductive program synthesis could be used to assist programmers in software development. So, for example, in the sketching framework, the programmer does not give a complete program, but provide a program sketch, a program with holes in it, which have to be filled with concrete code. And these pieces of code for the holes are then automatically synthesized by the sketching system. Or for end-user programming, inductive program synthesis might enable end users to generate their own small individual programs by providing some examples of the intended behavior. Then it might also be used to discover and invent completely new algorithms or optimize algorithms. And finally, in artificial intelligence and cognitive modeling, inductive programming might be used to enable intelligent agents to learn complex recursive strategies from initial problem-solving experience. Okay, and there I will have some examples at the end of the talk. Okay, of course, these are quite different application fields with quite different requirements with respect to synthesis time, resources, robustness, and so on. So, for instance, an end-user system should be very responsible and responsive and efficient and converging based on few examples, whereas for a system that invents completely new algorithms, it might be okay that it runs for hours or even days on a cluster of computers or so. Okay, so now in inductive functional programming, we have basically two general approaches. In the search-based generate and test approach, programs are just generated one after the other until one program is found that correctly computes the examples. So this is fairly simple and does not have hard restrictions. You can define very complex program spaces and just enumerate them. But of course, for real problems, it is often not practical because of the huge search spaces. And on the other side, we have the analytic approach, which classically works in two steps. First, for each I/O pair, a predicate and a trace is derived, where the trace is some expression that applied to the input returns the specified output. And then in the second step, recurrent patterns between the predicates and traces are discovered and generalized into a recursive function definition. And this is a very efficient approach because it does not rely on search in a program space, but is analytic. This is based on well-chosen examples and strongly restricted schemas of synthesizable programs. All right, and because the algorithm EUR2, which I describe in the following, strongly relies on this analytic approach, I just spent 3 slides to explain this in more detail. So the initial work was from a guy called Summers in 1977. And the general idea is that for recursive functions, the output of one input is computed by means of computing outputs for smaller inputs. So that induces some recurrent relations of the input-output examples. And the idea is to discover these recurrent patterns and use these for generating the recursive function definition. Okay, so in the very original approach, we induce Lisp functions, simple Lisp functions, over S expressions, and the primitives that might be used, or that can be used in the synthesized function definition are char and coulter and cons and nil for the empty list. So char extracts the first component of an S expression, coulter the second component, cons constructs S expressions from 2 component expressions, nil denotes the empty list, atom checks if an S expression is atomic, for example the nil, and T means the truth value true. Okay, as control structures we have the McCarthy conditional and recursion, and all in-used programs fit into this schema. So we have one function f of one variable x, and then we have a McCarthy conditional, so P1 to Pn are predicates over x, and f1 to fn are some expressions over char, coulter, and cons. These are the base cases of the recursive definition, and then as last case we have recursive call embedded into some context. That is again an expression over car, coulda, and cons. And we have this x substituted by some composition of car and coulda. So we make it somehow smaller. Okay, so this is a single linear recursive function over these primitives. And as I said, it works in 2 steps. So here are again input-output examples of our init function that returns the input list without the last element. And first, these predicates and traces are derived. And yeah, you can see that, for example, this predicate atom of coulda of coulda of coulda of x is true for just this input here. And then this trace, if we substitute x by this input, returns the specified output. Okay.
A parentheses coulda of x. What's that?
Yeah, okay, this is a short notion of composed coulda. So CDDR means coulda of x.
What's the A outside?
The A is the atom predicate. This is short.
Predicate.
Yeah.
Oh, I see.
So this coulda of AB gives you the empty list, right? The coulda is the B, and the coulda is the empty list, and atom of empty list is true because the empty list is just the only atom that we have in this language. Okay, and yeah, now I don't explain how this initial program is derived, but that it can be efficiently derived, and so that we have some unique initial program. This is based on the restriction to these primitives, so that we have, or for example, if we would have also the function appending to lists, then of course these traces would not longer be unique. Then we could express this also as an append of the lists A and B, for example. So, okay. Now then, when we have these traces, then we see that they have recurrent patterns. If we name these traces by F1, F2, F3, F4, then F1 of x is nil. And for the remaining traces holds that we can express them by const car x, this is the constant part here, and then by referring to the previous trace and substituting the x by coulda of x. So for instance, this const car coulda of x nil is just this previous trace with x substituted by coulda x. And this is a recurrent pattern between all these remaining traces. So we have this recurrence relation, and then we just inductively generalize it from I equals 1 to 3 to all I element of the natural numbers, so I can be any natural number. And then, yeah, now we have generalized this recurrence relation and can re-express it as a recursive function definition. So, okay.
So what about conditionals? What if the traces are not similar and you don't generalize like this?
If you don't find such a recurrent relation, yeah, then you cannot generalize it, right?
But do you have a story for introducing conditionals?
Well, this is a conditional expression. That means we have two predicates here. I see. You know, okay. So we have derived these predicates here, and all constant cases that do not have these recurrences here will be the base cases of the recursion, right?
This is beautiful. So on the left side you have implicit conditionals there.
Yeah. Okay. Okay. So okay.
This is required that you have all the i's up to a certain extent. So for example, if you left out the second case where you have length 2, does it require that or not?
Yeah. This is another restriction. So we have as a first restriction we had this restriction to these small set of primitives, and the other restriction is that we need I/O examples some set of consecutive I/O examples. So if we left out one of these examples and substituted by some, maybe the example for the 5-element list or so, then this recurrence relation would be broken and we could not generalize it. So this is another restriction of this approach. That it does not work on randomly chosen examples.
And is it also possible that you can construct multiple traces before you do the generalization step?
Yeah, the idea of the approach is that we can generate unique traces, so that we do not need to search in some space, but that these traces are unique. So therefore, the primitives are restricted to cons, Karl, Kudder, and nil. But of course, it might be possible to also allow for other primitives, and then the traces would no longer be unique, and then you have to search.
Is it a question of, is this the property of the specific constructs that you have, like Karl, cons, Kudder, that it is unique, or is it property of the nice examples that you have chosen in which there is no repetition in the elements? That's why you get these unique traces.
So yeah, it's both. It's based on the restriction to the primitives, and another restriction is that we cannot have the same element twice in the input list, because then again we would have non-unique.
So what you're doing in the top, number one, is you have these examples, and then for each example you derive this little program, and then you do this generalization step to basically get the base case and the inductive, right? So in those programs, so I guess you never refer to, so the only atom you have is nil, so you're not allowed ever to refer to one of the constants on the left-hand side?
Yeah.
I see.
I just checked the structure of the input. Yeah. Okay, so there are many restrictions one can say to have this work, and and the idea now for the algorithm that I developed, the IGOR2 algorithm, is to somehow combine these both approaches: a search in a program space with this analytical approach, in order to have some trade-off of expressivity of the generate and test or search-based approach and the efficiency of the analytic approach. Okay, and so if we allow for searching in a program space, this circumvents the strong restrictions of the analytical approach to a large part. For example, IGOR2 is able to use predefined functions by the user and not just these primitives, Karl, Kudder, and cons, and so on. And it is able to automatically invent recursive subfunctions, for example. There's no restriction to linear recursive functions, and the user may define any algebraic data type instead of using only S expressions. Okay, and but we still derive the candidates in the search from the examples, so large parts of the problem space are pruned. Okay, this is the general idea, and and the functional programs that are synthesized are represented as a sort of term rewriting systems. So, particularly by constructor systems, and not only the synthesized programs, but also the I/O examples and the functions that are predefined by the users. They're all represented as constructor systems. And a constructor system, CS for short, is just a set of equations interpreted from left to right as rewrite rules over a first order signature. So we exclude higher order functions here. And a constructor system means that the signature is divided into two parts: the defined functions D, which are those function symbols that denote the functions that are implemented by the program, and the constructor C, which basically define the algebraic data type, so the values of the domains of the functions. And then the rules have the form F, where F is a defined function of arguments P1 to Pn. this need not to be variables, but could also be terms, but only terms including only variables and constructors. So this is the usual pattern matching in functional programming. And then a term T, the function body. Okay, and one restriction is that each variable here in the function body need also occur in the function head. Of course, that's clear. So to have a function. Okay. And now the problem is given an example CS, so given some input-output examples. And the input-output examples need not to be actual examples, but can also contain variables. So can be patterns of examples. But okay, I forgot one thing. The example in an example constructor system, the right-hand side also is a constructor term. So this is a restriction for the examples. They may have variables in it, but they do not may call functions in their body. But the body need also be a constructor term, so a value basically, or a pattern for a value. Okay, so we have an example CS and a background CS, which includes the functions that are predefined by the user that can be used in the synthesized program. And then the problem is to find a CSP such that if f of I1 to In to O is an IO example, so it's included in the example CS, then the inferred program P together with the background program shall reduce I1 to In to the specified output O, right? So this is the problem. So we want to find some constructor system that correctly computes the examples together with the predefined background functions. Okay, and the general approach is to apply a uniform cost search in the space of orthogonal constructor systems. So we initially, at first we derive some initial candidate, and then at each search step we choose some of the maintained CSs, and if it is acceptable, then we return it as solution, and if not, then we apply some refinement operators to the chosen CS, and that results in a set of successor candidates, which we replace for the chosen constructor system. Yeah, and then the search proceeds until we have found some acceptable CS. Okay, and the costs of the candidates are defined by the number of disjoint patterns, and the rationale behind that is that we want to prefer programs with fewer case distinctions or with fewer conditionals, right? So to get a most general program that computes bigger subsets of examples by the same rule, actually. Okay. And the construction of the candidates is analytic. That means that each constructed candidate is correct in some sense, so subsumes the input-output examples. Okay, so this relation here basically is this constraint. So all candidates are correct, but the candidates may violate this condition here that all variables in the body need also be defined in the head. So we may have some candidates that do not represent functions. Okay, and those candidates are not acceptable as solutions, and if we choose such a candidate, then it must be refined. Okay, yeah, and the acceptance criterion is just that a candidate has not such open variables, and then it is correct and correctly computes the examples, and is a solution to the problem. All right, so okay, now given some input-output examples or some input-output patterns here, again for the init function, first of all, we generate one initial hypothesis or initial candidate. And this consists of just one single rule for all the input-output examples. And this needs to be a rule that subsumes all these examples, so that can generate each output from the corresponding input. And this is done by taking the least general generalization, a syntactic generalization. This is a concept defined by Plotkin in 1970. And the idea is that we just, at each position where the examples are equal, we just keep the position in the symbol. And at each position where the examples are different, we introduce a variable. So for example, here we have, at this position, we have the empty list in the first example and the non-empty list constructor in the second and third example. So we introduce here at this position a variable. And the same for the right-hand side here. And this is another variable, a different variable from the first one, because the terms in the examples are different ones, right? Okay. So now we have an initial rule. We have just one rule that covers all examples, but which is unfinished due to this open variable here. So now we need to somehow refine this candidate and to eliminate this open variable, and we have our eager2 defines 3 operators to do this. So the first operator is to split such an initial candidate into more than one rule. So to introduce some case distinction or conditional. This results in a set of new rules with more specific patterns than this original pattern, which are disjoint, so which basically somehow partitions the domain. The second operator separately deals with open subterms in the function body, and by introducing new subfunctions. So this is an opportunity to invent recursive subfunctions. And then the third operator replaces the right-hand side of an unfinished rule by a call to some previously defined function. That may be a recursive call, or a call to a predefined function, or whatever. Okay, so now the first operator, splitting a rule. Okay, here are again the 3 input-output examples for the init function. This was the initial rule. And now this operator works by choosing one position in the head of the initial rule, where this rule contains a variable, and the I/O examples contain different constructors at the same position. And then we just partition the examples according to these different constructors. So the first example goes into one subset because it has an empty list here, and the other remaining 2 examples go in another subset because they have non-empty lists here. Okay, and then we just compute an initial rule for each of these subsets. These new rules have more specific patterns than the initial rule, and the patterns are disjoint because they have different constructors here at this position. And and the first rule just reproduces here the first example in this case, and it's the base case of the recursive function. And this second rule is again unfinished because it has here again an open variable ys. Okay, that's clear. Okay, then now the current candidate is these 2 rules. And now we might apply the second operator, because we have now the open variable here as a proper subterm of the function body. So we can think of this first component here is just solved because here's a variable that is defined in the function head. So this part of the function body is solved, and we just look at the unsolved part and try to consider this as a new subproblem and introduce a new subfunction which just tries to compute this remaining part here. Okay, so the unfinished rule was this. Then we replace this open variable by a call to a new subfunction, applied to the same input than the initial rule here. And then we derive I/O examples for the new subfunction just by taking the same inputs, because the pattern is the same. So here are the init examples and the examples for for the subfunction have the same inputs, and the outputs are derived by just taking the subsets of the init examples. Okay, and then if we then induce a function for sub1 that correctly computes these examples, then also this rule is correct for the init examples. Okay, then at the first step to induce the function for the subfunction, we just again compute the initial rule based on these two examples. Okay, resulting in this rule, which again is unfinished. So now we have, this candidate here. Two rules for init with the call of the subfunction and the subfunction with the initial rule that is unfinished. Okay, now the idea of the third operator introducing function calls is, or how does this work, where we just choose a defined function, f prime. So if the unfinished rule is f p1 to pn to t, then we choose some other or the same defined function f prime, so that each right-hand side of the examples for the unfinished rule is an instance of some right-hand side of an examples for this chosen function here. And then we generate arguments of the function call by which maps the left-hand sides accordingly. So, okay, so this is actually the same idea than finding these recurrence relations in the original analytical approach. We just match not traces in this case, but directly the specified outputs. So for example, we have here the okay, we want to finish the rule for sub1, and we choose init as the called function. And now the question is which argument has to go here. And therefore, we match the outputs of the sub1 examples to the outputs of the init examples. Okay, here it is actually just the same. And here we have a variable replacement. And then we can compute this example for sub1 by a call to init, and the argument need to be this this input for init, right? So if we want to replace this output here by a call to init, then we need to come from this sub1 applied to x, y empty list to init of some variable empty list. Okay, and the same here. Okay, and now we have to merge these two rules into this target rule. And if we choose this argument here, then we have these mappings here. Okay, I think yeah, we'll have to do, yeah.
In this case, if the definition of a new function is not an invocation to an original function, but say composition of two original functions. So is this something that you can also search over? So maybe let's say sub1 was not some call to init, but some call to init, composing some other call to init, and then you take the composition of the values.
Yeah. So some nested or some composed function.
Yeah,
that's possible. Yeah, that's possible. So if we do not find here such a constructor term, this is as argument. Now we have found a constructor term that is just a term composed from the constructor here and some pattern values, right? And if we do not find such a constructor term here as argument, which maps the left-hand side together, then we introduce the call of init, but as arguments we again invent new subfunctions. So then we would have a new subfunction sub2, and would generate and would have these mappings of the left-hand sides from sub1 to init as new input-output examples of this new.
And then you do the search in some depth-controlled manner so that you can also try
right.
with the breadth.
Right.
Nice, very nice.
Okay, so this is the simple case of this function call introduction, and we have this more complex case, right? Okay, so now we have this candidate here, and this is now finished because in all the function bodies are only variables that occur also in the left-hand sides, and we are done, and this is a correct implementation of the init function. And as a post-processing step, we could unfold this non-recursive subfunction, unfold it here in the body. Right, okay. So this was a very simple example, and instead of only one target function in it, we may have several target functions that may also be mutually dependent on each other. And here in this example, we didn't have predefined functions, but just constructors. So we may have predefined functions for more complex problems. And induced subfunctions like the sub1 here may again be recursive. And that was the problem you mentioned. If the function call, for a function call new suitable constructor term is found, then we can also here invent a new subfunctions to compute the arguments of the function call.
So in the first bullet, when you refer to the word parallel, are you also hinting at the implementation details here that we can also parallelize this algorithm, or?
Sorry.
So when you refer to parallelization in the first bullet there, parallelization. Parallel?
He means he can do both, even and odd. So he will synthesize more than one function at the same time.
I see. Okay.
Yeah. And now, we went quite straightforward to the solution here. Actually, at each search step, all three operators are applied, resulting in more than one successor candidate, and then we might have more implementations, different implementations of the same function, right? Yeah, okay. Some properties of eager2 are that it is terminating if we bound the maximum depth of function compositions, and the search is complete with regard to the problem space, which is defined by the initial candidate and the synthesis operators, because we apply basically a breadth first search. And the generated programs are correct by construction with the examples. Okay, what we not have yet is precise characterization of the class of functions that we can synthesize. Since you can give predefined functions as background knowledge, you can, if you allow arbitrary predefined functions, then you can just give the function to be synthesized as predefined function, and then you are complete. Then you can infer each computable function. But if we have no background knowledge, so if we just synthesize a function from scratch, then we have the following scenario that we are not complete with respect to primitive recursive functions. So the design of the synthesis operators exclude some primitive recursive functions to be synthesized. On the other side, we have some non-primitive recursive functions that are inducible, for example, the Ackermann function. Okay, so we have done some experiments with a prototypical implementation in the mod language of eager2. And we first tested a couple of list processing functions as defined in standard libraries of Haskell or ML. So init, last, append, length, reverse, take some number of elements, drop some number of elements from a list, split a list into two lists at some position, zip two lists into a list of pairs of elements, shift a list, or weaving a list of lists into one list, and so on. And also for some benchmark problems in problem solving, like Towers of Hanoi, or blocks world problems, like building a tower in a given in a specified I missed the word in a specified order. So you have, for example, 4 blocks and want to stack them together in a tower in a specified order, or delivering problems such that the rocket problem. Okay, and we see that we also compared IGOR2 to some other systems, and for instance, compared to former analytic methods like the original one by Summers and also a predecessor of IGOR2, we found that more functions can be induced, so the space of inducible functions is greater, and often this is more efficient than applying generate and test methods. Adati or Magic Haskell are 2 generate and test methods to infer functional programs. And compared to ELP, so inductive logic programming systems like FOIL or Golem, the solutions are often correct, where for ELP systems often the solutions, they find some solutions, but they do not implement the intended functions.
I thought your solutions are always correct.
Yeah, okay. Correct here is correct is meant with respect to the intended function, and not just to the given examples. Okay, so a slightly more complex example than init is the reverse function. If we synthesize reverse from scratch, so just given the input-output examples here, then IGOR2 comes up with this solution, where it has inferred 2 sub-functions, sub1 and sub2, which are the function that returns the last element and the init function. So, and then the solution for the recursive case is for a list of 1 element in the rest list is take the last element from the list and put it in front of the reverse of the init list. I mean, this is not a very efficient implementation, but a correct one at least. Okay.
So, I'm sorry, I missed the beginning of the talk. Maybe you already answered this. So how do you decide how many input-output examples are necessary? Like in this case, with the 4, it seems like the 4 is redundant. Yeah.
I mean, yeah, in general, you do not know the number of examples you have to give, but one restriction is that you need to give somehow a complete set of consecutive examples, just like in the original analytical approach, because of this data-driven or analytical approach to synthesize the functions. So I mean, if you give, for example, an example for the 4-element list, then you also need to give examples for the 3, 2, 1, and empty list.
Right, but what about if you didn't give the 4-element list? Would it, in this case, would it work if you only had the 3, 2, and 1?
Only 3 examples, or what?
Well, if you didn't have the list with 4 elements, you just had the list with 3.
Okay,
would the solution still be correct?
Then, in this case, IGOR2 inferred some non-correct solution. So it inferred some generalization of the examples, but this function didn't implement the reverse function. So there, or at least not only the reverse function. In this case, it converges to this solution, and there is no other solution with the same cost or with the same preference path. But if we cut this example, then there is a couple of different solutions, among them this solution, but also other solutions which do not compute the reverse function.
So on that note, one trick that I can share with you here is, which you did in our synthesis of bit vector programs, is that since examples are an incomplete specification,
right.
And what we try to do is to see if we can find at least 2 different programs that are consistent with the same input-output pairs that are provided, and then we can generate a distinguishing input for those 2 different programs, because those programs are semantically different, and you can go back to the user and say, look, the specification that you gave me generates 2 different programs which have similar costs, But if you tell me what is the output on this input that distinguishes these programs, I can do a better job at selecting between them or finding at least some other program which is consistent. So that trick actually worked quite nicely for us in the bit vector synthesis, and we might consider applying something here as well.
Yeah. But I mean, okay, at some level though, without a general characterization of the result. So in this case, there is a constraint that says that the input elements are related to the output elements in a very specific way. I mean, you could imagine a program here that just gave you exactly those outputs for those inputs and null for everything else, for example. I mean, that's not a particularly interesting program, but it would satisfy the set of examples.
But it will have high cost because to write such a program, you have to write lots of if-then conditionals. Right?
No, right, yeah. So it's not the best such program by any definition.
But that's the only way to rule out such programs, because otherwise the problem will always remain undefined and uninteresting, because you can always say if the input is I1, then the output is O1.
Right, no, but what I'm trying to say is not only so in this so it's interesting because there is a connection here with the the string processing or whatever, but at a high level I think it goes back to the question of not only giving a program but an explanation of what the program does in some sense, and in this case for a programmer specifying that the output is the reverse of the input for all such inputs and outputs in some formal terms could be consumed, right? So the high level question is, can you infer, postcondition from the code that you generate that you could show to a programmer and say, this is what we generated. This is what we intended. Yeah.
Some specification of the inferred program.
Yeah, exactly. Right.
That might be more complicated than the program itself.
Maybe.
That's a fair point.
Programmers are pretty good at looking at code and seeing what it does.
You show the program. Okay, that's a fair point. And it's functional. So
you mentioned that this is the specification.
Yeah. Okay, that's a good point. Okay.
The program itself is often the most concise form, especially for simple.
That'll have you believe.
Okay, here. So we may, if we give, in addition to the reverse examples, also some examples for a append function, appending to lists, these ones here. Then eager2 comes up with this implementation, so using the append function, for example.
Is there any way you can synthesize an efficient reverse, like a linear cost reverse?
Yeah, I can synthesize this reverse here with this reverse. Yeah. But this is synthesized if I specify this parameter also in the examples. So
you give me the right signature to begin with.
Yeah.
That's very cool, actually.
Yeah, that is.
It would be better if it is found automatically. So if the second parameter is inferred automatically, but okay. Yeah. Okay, and here's a more complex example: swapping two elements in a list at specified positions. And restricted us to cases where the first index is smaller than the second one, and where the indices are different, and where the list actually contains these both indices. Okay, then we gave this 6 examples here, and eager2 synthesized this solution. So if we want to swap the first 2 elements, this is easy. This is just the base case, and also the third case is fairly simple. If we want to swap two elements at some indices n+1 and n+2, then we just keep the first element and apply swap recursively to the rest list and decrease the indices by 1. Okay, this is simple. Okay, question?
So in this case, do you actually infer the preconditions on the inputs explicitly, like that the numbers, the first number is smaller than the second number? And that the list is of a length smaller than the indices.
Yeah. We gave only examples for these cases. Yeah, right.
But in terms of solution, does the solution have those automatically inferred?
Yeah.
Okay. So those could be preconditions on the solution where if you could raise an error if it fell outside those boundaries, right?
Mm-hmm.
Okay.
Yeah.
So that's a form of documentation about what the intent is.
Okay, so and for this second case here, we have two nested recursive calls, right? Is that clear? This second case, or okay, okay. Once here's an illustration. So we want to swap the first element. of index 0 and some other element in the list at index n plus 2. So, and how do we do that? We just extract the second element from the list, the x1 here, put the first element in front of the rest list, then we swap again these two elements, the inner recursive call here, and then this is the result, so where these elements are swapped, and then we put back the second element to the front of this list and do another swap on the first two elements here. Okay, and then we are done. So this is, I think, a nice, bit more clever thing than just reversing a list, so which automatically could be synthesized. And here's another more complex example which works on a list of lists. So we have a list of some inner lists. And the function is called Reef, and the task is to take the elements from the inner lists in some rotation. So first the first element from the first list, the first element from the second list, the first element from the third list, and so on. Then the second element from the first list, the second element from the second list. So, okay, and this is the synthesized solution. Reef from the empty list at the empty list, and Reef of a list which contains at least some inner list. So we have one list and some rest list of lists, and then we take the first element of the first list and call Reef recursively on what? On something that is computed by sub 36, and sub 36 just rotates the inner list. So just puts this list at the end of the rest list and cuts the first element here. Okay, and it does that by going recursively over this list of lists and just so somehow bubble the first list to the end of the list of lists. Okay, here's an example of where we have specified two target functions, odd and even, over natural numbers this time. And the synthesized solution is this one, where odd calls even and even calls odd. Okay, so and here's another problem, the towers of Hanoi, where we have given examples of the solution trace, so of the solution plan for one disk, for two disks, and for three disks. For example, for 3 disks, you have to do 7 steps, 7 moving steps. And this was this example here specified for eager2. So we have a number of moves. The first argument is the number of disks, and then these are the 3 places, and S denotes a state, or to compose these moves. And then eager2 came up with a known strategy for towers of Hanoi.
So do you have any hope of synthesizing this program if you don't give the trace as an input, but just give the initial and final configuration and have some other way of specifying the constraints of what block can be put on top of what?
Yeah, that is the idea for future research, that we integrate eager2 into a planning system. So we have a planning system where we just specify the problem of the towers of Hanoi, and then let the planning system generate the plans for some simple problems, and then we have to somehow translate this to examples for eager2, derive the recursive strategy, and then the idea is to re-express the recursive strategy in terms of some form of background knowledge that can be used in existing planners. So for example, hierarchical task networks or so.
I had a question about the previous slide. Can you go back just to the previous slide? So, actually, the one before that. There was the one with the sub-problem, which was the rotate. Mm-hmm. It seems like once you know, I mean, in some sense, rotate is like a primitive. And the question, I guess, my question is, could you, if you've already synthesized that before, could you remember that you'd done that? And when you see a case where you need to rotate, you just, instead of resynthesizing, you actually just pull it out, essentially. Because once you have a piece of code, you know it's input-output behavior, right? So you can somehow match a desired input-output behavior to a known one. And I don't know if that would be faster, but it seems like...
yeah, in general, it would be faster if we just gave this appropriate function, this rotating function, then the solution would be found faster. That's true. So we could, in the first step, infer this rotation function, and then give this function or the input-output behavior as background knowledge for the Reef function. Yeah, and then that would be faster. On the other side, if we give too many functions that could be used, then this results in a bigger search space, right? So then yeah, if we have more than this functions with the same type, so such that it could be useful, then it has to be figured out if it already works. So then this makes the search space greater. Yeah. Okay. Here's just a plot of searching for a solution for the towers of Hanoi versus computing it with the inferred recursive strategy to see that it is useful. Okay. Okay. Here another problem in the cognitive modeling area was building a tower in the blocks world. So we have some blocks lying on a table stacked somehow together, and we want to have a tower of or a goal configuration, where in this case 2 specified blocks are stacked together in some given configuration. Okay, so this problem has also a recursive solution. If we have a tower up to some maximum number of blocks, then we have to build the tower with except for the highest block, and then we need to clear the last block. So we need to put to the table some blocks that are above the last block, and then put it to the tower. So this is basically the recursive solution here, and that could be inferred from, in this case, 9 examples with the function that clears a block given as background knowledge. Okay, so that basically was it. So the conclusions are that I think the idea to combine this search in a program space with some analytical methods to generate candidates can help to expand the set of practically solvable problems. One observation is that the efficiency or effectiveness of Igor2 highly depends on the structure in the examples. So if the examples do not contain some structure, then we have many ways of mapping or matching the examples together, and then we have again effectively an enumeration of the space of programs. And what we already did is an extension to higher order functions, so where we can predefine higher order functions like map, filter, reduce, and then use these as background knowledge, which can be helpful because then the synthesized program becomes more compact, so can be found with fewer induction steps. And also this helps to better characterize the class of synthesizable functions.
But you can actually synthesize the higher order function itself, right? Just using them.
Yeah, just using it, yeah. Mm-hmm. Okay, and some ideas for future work is to deal with missing information. So if we do not have consecutive examples, but randomly sampled examples, or where the examples have errors, to deal with that. or to not infer a function from scratch or with background knowledge, but we may have the case that also the target function is somehow partially defined, or it is defined but has some bugs in it, and then to fix it. Okay. And currently we are applying IGA2 for automated planning. I explained that in the case of the towers of Hanoi, and cognitive modeling. There are similar problems. However, in cognitive modeling, there are issues like cognitive plausibility and how the symbols can be gained from non-structural sensoric information. So those are other problems that are not directly related to the actual program synthesis task.
So
okay, and that's it. Yeah.
A bit more about the cognitive modeling application. So exactly what is cognitive modeling?
Cognitive modeling is that's the modeling of the human mind, basically. So the idea is that inductive programming can model the capability of the human mind to acquire concepts or strategies for problems that are basically recursive, such as towers of Hanoi or some other concepts. Yeah. Okay. Thanks.
Do you see the application of this to actual developers? I mean, it sounds like you're sort of taking this down the path of, sort of using it to help as a tool in a toolkit for more AI-related tasks.
Mm-hmm.
But I guess the high-level question is, could this be useful to somebody who just wants to write code?
Yeah, I think.
And how would it be used? And what would the model you could see be?
Yeah, I think it could be useful. So to not to generate complete big programs, but to synthesize single functions or modules also from examples.
So is it your interest to pursue that direction, or is
yeah,
okay.
Yeah. And again, and another application area would be end user programming. So end users that are not experienced with programming, but who can express what they want by examples, right? That is a good application area, I think. And for professional programmers, I thought that probably the test-driven development framework might be a good starting point, because there one has tests at the first instance, and one just could use these as a kind of incomplete specification of the problem, and then use a synthesizer to synthesize some prototypical code or something.
Because it gives you counterexamples. Put it in, and then well, not all.
Okay.
See how many it could solve.
Yeah, actually, that's true.
F-sharp. I mean, it's actually it just has to generate the right.
Well, but it has to have an oracle, which is the hidden program, which means you already have solved the problem.
So I have a follow-up question on what Ben asked earlier, which was about adding more background knowledge. So you mentioned that there is a trade-off between having too much background knowledge and having too little background knowledge with respect to the search becoming huge and so on. So do you have a sense of what is the optimal point like, or how should we define that?
Yeah, in the case of IGA2, it is the thing is that if you give background functions that can be used for the solution, then it helps. If not, then it directly results in.
So the real question is that let's say you have a huge collection of functions that other people have developed and so on.
Yeah, so I think
should you keep them in the library, or should you not keep them in your library? Because the user does not know.
Not for IGA2, but in general, yes, I would say so. You have to you have to develop some method to somehow, or some heuristics or whatever to pick the right function from the library, right? That would be good, because if you need to give just the correct function, I mean, then you need to have an idea of the solution. So if you want to give just the suitable background knowledge, so the better way would be to just provide the library and say, okay, here these functions can be used, and then you need some way of managing this, right?
Any more questions? Okay, so let's thank the speaker again.
Okay, thanks. Thanks.